Welcome to solverfy.
In this problem, we have a little contraption here where we have a angle here pivoted at the corner, and there's a mass attached to this end of it, and then a spring supporting it down at the other end. And at the opposite end of the spring, there is a contraption that causes an excitation, a harmonic excitation at the end of the spring that's away from this end. So we have our spring force here, we have our gravitational force, we have our reaction forces at the pin. Take moments about point A, and we get the moment caused by the spring force, the moment caused by gravity, and then we're told that to neglect the mass moment of inertia of this bar as compared to the moment of inertia contributed from this block, which is 2mL2 squared theta double dot, and this is L2, and I've said this is L1. Now, in this case, let's see here, we have, I guess I didn't write down what those were. So L1 is 1.2 meters, and L2 is 0.6 meters. So the mass, we were told, is 4 kilograms. The spring constant of this spring down here is 15 newtons per meter. And the excitation frequency is 15 radians per second. And its amplitude is 100 millimeters. So this is our excitation. So the spring force, and again, this is approximate because I'm using small, I'm assuming that the angle here is going to be small, so that the displacement down here is roughly L1 theta. So we also have some pre-compression in the spring if we're going to measure theta from equilibrium, and that would be because this thing has some weight, and if before we have any excitation on it, it's going to cause this thing to sag a little bit and pre-compress the spring. So theta is being measured from that equilibrium state. So we have this static deflection in our deformation in our spring, and then on the other end we have some excitation. Now we can plug this into here, and again we're going to see that the static deflection and this gravity term will cancel out, and in fact that's the static deflection is defined so that they do cancel out. Now, our equation of motion then becomes mL2 squared theta double dot plus KL1 squared equals KL1 times the excitation. Plugging in our values and dividing through by this thing, we get theta double dot plus 15 theta equals 1.25 cosine 15t. And we were asked to determine the steady state amplitude. So the response, determine the steady state, So the steady state response, or the particular solution, is, let's see here, is 1.25 divided by omega n squared divided by which omega n squared is 15, the forcing frequency is 15, so we need to square it, so we get 15 minus 15 squared, and then cosine, because this was a cosine here, cosine 15t, plugging in values, this becomes, let's see, this is minus 5.95 millimeters, and so the amplitude, and this is negative because the excitation frequency is greater than the natural frequency. So we get the magnitude, we just take the magnitude of this, because eventually this is going to be a -1. And so, I said this was meters. This should be radians. And so the amplitude is 0.00595 radians. And they actually wanted the amplitude of the motion of the block. And so we know the motion of the block here is roughly L2 times theta. So that's the geometry says L2 times theta is the approximate motion of the block if theta is small, which it is. And so we just multiply this theta max by L2 to get Y max, and that becomes, let's see here, 3.57 millimeters. So it's moving quite a short distance, which is obviously quite a bit less than 100 millimeters. And why that is because our forcing frequency is so much greater than the natural frequency. This denominator is pretty large, or the absolute value of the denominator is quite large. So we're getting a lot of attenuation. Basically, this thing over here is moving so fast that this thing has really no time to respond to it because of its mass.